Can we start now? Okay, great. Thank you very much, Marcy and Aaron. I'm very glad to be here to present our lab's technology. But we know here today it's a special day. I'm the first time to present in front of just two of you, and I know many people are watching online. Is to face the COVID outbreak situation, so everyone can understand. But anyway, I feel like I'm the first one, right? So everyone want to be the first, so here I am. So hopefully the effect is okay. So today I'm going to talk about actually I'm going to have coronavirus as my example. So because my lab is doing some coronavirus work. The title of my presentation is Ontoanimal Tools for Extensible Ontology Development. So we call it XOD. So it's like an extensible markup language, XML. We have XOD, browsing, query, and data fairness. So myself, I have been with the DCMB. I think the CCMB is part of DCMB, right? So for many years, starting when I joined Michigan 2005, my primary appointment is in the unit for lab animal medicine, and I also have a joint appointment in the Department of Microbiology and Immunology. So my bachelor degree is actually veterinary medicine. So I was a veterinarian actually for a couple of years, and then I did some master research on some virus, some retrovirus. So as we know, the SARS and the SARS-CoV-2, which causes the COVID-19, they also are retrovirus. So we do find some commonality. And then I came to the States 1996. I did some zoonotic disease research focusing on vaccine development. It's a bacteria, it's not a virus. It's called brucellosis, so which can cause human problem and animal problem. And then I had my master's degree in computer science after my PhD. And then I worked at the Virginia Bioinformatics Institute for 3 years, and then I came to here. So in the Virginia Bioinformatics Institute, actually I developed something called PIMO, it's pathogen information markup language. So actually we talked about those viruses and bacteria. So but anyway, so I feel like I'm a good fit into the outbreak because that's what I studied for a long time. So actually, my outline in here is like this. So I'm going to introduce what is ontology and how ontology can be useful actually for studying, for example, kidney, precision medicine, or study coronavirus, infectious disease. And then I will say, okay, ontology is good, and we need to build interoperable ontology to support this kind of disease analysis and many other things. And then, is to support the data fairness, right? So data fairness is, more like the recent movement initiative to make the data like a findable, FIND, interoperable, accessible, usable, something like this. But anyway, so, and I will argue ontology is key, to the whole data fairness. And then to study the data fairness, we need the interoperable ontology, not only ontology. And then how we do interoperable ontology, then we have XOD and we have tools. So this is how everything comes together. So just give some background. I think that, this kind of background for the audience here bioinformatics probably is trivial, right? So we say, okay, the bigger data is more like 4Vs here, and people sometimes use a 3V model, 4V model, or 5V model. The 4V model is basically volume, variety, veracity, and velocity and veracity. So they're talking about the different aspects of data. So currently the data is very heterogeneous and definitely not easy, right? So as the Nobel Prize winner, Sidney Brenner said, we are now drowning in a sea of data. But often we get no results, no knowledge. So we are searching for knowledge. How can we do it? How can we get from this kind of messy, often bigger data for knowledge, right? It's a bigger challenge. So just give some example, like so for example, we have 2 hospitals. So they have different data database, right? Patient data. So you can see this is their patient index, disease code, disease name. Well, you can even see, okay, I have the same name but in different language. So you can see it's not easy, Like for example, you can find a lot of synonyms, like iron deficiency anemia and cytopenic anemia. They basically mean the same thing, but you give it different name, right? And then you even have different code. Of course, there's Chinese, they are different as well. So if you want to ask a question like how many patients in here, even the 6 people here, who have anemia, not easy, right? Or yeah, what we say who have anemia is basically anemia is more like a higher level because there are several anemia. They are more like subclasses. They are subset of anemia, and then the naming are different. And then so a lot of issues here is just like an example. So in real hospital or real biomedical data, something like this is the same. So it's like different data resources, how to achieve data sharing and data operability. And then how you can do like inference, right? Like who have anemia. So it's a simple inference. You just need to make sure you know which one is anemia, right? That's no exact kind of disease name which equals anemia, but they are more like a subclass of anemia. So often these kind of things can be quite challenging. So here again, like for the big data analysis, often we see 80% of data they are more focused on, time when you analyze big data is more like the data integration part. So we argue, like the ontology is a major foundation for the data integration. Yeah, so the premise is findable, accessible, interoperable, and reusable. Of course, there's interoperable. So I want to emphasize interoperable is the key here. So I also want to say like AI, right? We're talking about AI a lot. So what is the foundation of AI? So just give one exercise. So let's say we have some question like, you are talking to an AI machine, right? Robot. Oh, I'm a human. I'm sick. I got a kind of COVID-19 or TB or whatever. So how should I do? I'm kind of stressful. So when you talk about to a robot, right? So the robot is AI now. Robot is very intelligent, right? So what they should do? They should understand you, right? They should understand. Oh, you are human, right? So what is human? You are kind of you got maybe TB or tuberculosis or virus. What is TB, right? What is virus? So it's like it's not only the meaning. It's say, oh, I know you, but no, you need to know more, right? So I will say, okay, I'm a human, and the other guy is a monkey, right? So the robot should kind of quickly understand the relationship or difference, similarity between me and the other one, right? So what's the difference between human and the monkey? So this is how the artificial intelligence should take care of, right? So in this case, so the key about AI is like the AI should know the meaning of words, right? And the relations among the words. So it makes sense, right? So we want to say AI. So here I want to argue like ontology will become the basis of AI. So what is ontology? So onto means being, means reality. So ontology basically is more like a branch of science studying being and reality. So originally it's more like a philosophy, right? It's like what is the nature of me or the universe or everything. But now when it comes to IT field, so the definition is can be defined as this way. So ontology is a human and a computer interpretable representation of entities and relations among entities in a specific domain, like a disease or universe. So in here, the keywords is computer should understand. So like AI should understand, right? Human, of course, should also understand. And it's interoperable, and it's a formal logical representation. So here, so just looking for the question I gave earlier. So let's say I talk to a robot. I say I got sick, I probably get COVID-19, right? So robot, if a robot is smart enough, right? Let's assume there's a super robot. They just know everything. So they say, oh, I know you. I know what you mean here. So what it means is the COVID-19 is caused by the virus, right? This is the virus. And then, yeah, you are human, right? So, yeah, so the COVID-19 actually can infect a human. And like your lung probably has some issue. So yeah, so the kind of pathological location can be the lung, and lung is part of a human. So what's the similarity, or what's the difference between human and the virus, right? So they are more like organism, or like virus, particularly it's not an organism per se, but it's more like a in between organism and the non-organism. So virus definitely cannot survive without the cell, right? But virus, they can infect, they can replicate. So yeah, if you have something like this, if you give this one, so we can call this one as ontology, right? Because it fits into ontology's definition. So you can, if you give this one to the AI becomes smarter than before, because now AI is more than as, oh, I'm a human, or you get a disease, right? So AI can know the relation between you and the disease, and the cause of disease, and everything can be linked together. So if we can fit into AI robot into something like ontology, or you can give different name, maybe knowledge graph or some other name. So the AI becomes smarter. So basically, AI, you can see AI includes two major branches. So one branch is machine learning, right? Another branch is knowledge representation and the knowledge kind of reasoning. So ontology basically is more like the formal representation of knowledge. So it is a key part of AI. So if you look for different aspects or different technologies or range of sciences, you can find this one. So like the ontology is up here. The technology is called OWL. So OWL means Web Ontology Language. What they change a little bit. You should say WOL, right? But just say okay. OWL is more like animal. So this is technology. And then the other side is more like the methods or the entity or the science. So basically, you have a dictionary, thesaurus, control vocabulary. You have data model, taxonomy, and ontology is more like more advanced. But definitely, it's like you use advanced technology, also you got to suffer, right, some cost. So what's the cost? You need more time and more money to develop ontology. Yeah, but however, the semantic precision is much better. So you have a better kind of reasoning power, and the machine can understand logic and can understand more. So that's very important. So let's say if you have Excel table, so you have column, you have rows, right? So it's more like a dictionary. You say, okay, I have different, each row is a term probably, and then you have description. But however, it's like the relations among terms probably is not defined. So ontology can define the relations among different columns and among different rows. So ontology definitely give you more semantics for the more advanced study. So yeah, so basically, roughly you can see ontology equals controlled vocabulary plus relation or semantics. This is just a rough one, but I did give the exact definition earlier. So yeah, if you do the gene expression analysis, so most likely you are going to use the gene ontology, right? So gene ontology was developed in the end of last century. So when kind of people at that time, there were several many like organisms genomes sequenced, like human, mouse, plant, fish, and bacteria. So then they say, oh, we should annotate the genes, the genomes. The genes is so hard to annotate if you just imagine what happened that time. So how do we annotate? And then eventually they say, oh, I should work with you together. I'm working on human, you are working on mouse, or you are working on zebrafish. So we should work together. So the joint forces to generate the gene ontology. That one can be used to annotate different genes. Exactly, it's gene products, three components, right? It's like a molecular function, biological process, and cell component. But just this annotation is so powerful. So people are using it all the time. It's not the default approach for now. So then people are wondering, we should have ontology for many other things. I did vaccine ontology. I'm doing the kidney, cell line, and adverse events. And now I'm doing the coronavirus disease ontology. But anyway, so we can use ontology not only gene products, but everything. So that's kind of the idea. Okay, so this is some background about ontology. So hopefully you have some basic understanding, or maybe you already have basic understanding, just to refresh your mind. Questions? Any questions?
No.
No?
Not yet.
Okay. So I'm going to put the second one as a whole. So yeah, I'm going to kind of put my demo kind of intertwined inside the technology. So I'm going to have two demos. So one is the kidney tissue atlas ontology. So this ontology actually is getting big. It's one essential component of the so-called KPMP, the Kidney Precision Medicine Project, which has been funded by NIH and involved like more than 20 communities. So we just submitted a paper and got a feedback, got a review back. So it's in the Nature review. Nephrology is one of the best journals in the field. Yeah, so it's very exciting for us. And then I'm talking about the CIDO. This is the coronavirus infectious disease ontology. So that one I just initiated about 1 month ago. So because we had this coronavirus initially in outbreak in China, and now kind of spread out everywhere. And yesterday, the WHO announced it to be like a pandemic, like everywhere it's coming, it's emerging. So, so really, you can imagine the coronavirus, right? The data associated with the outbreak, can imagine they fit into the bigger data category, right? So they are heterogeneous data. They have bigger value data, a lot of deaths, unfortunately, in the people, and then the disease, the virus, and the human. It's a lot. So ontology is a very nice, it's a very good fit to analyze them. So you can think of ontology as more like can be used as more like a data standardization, like a metadata standardization. Or can use it for knowledge representation. So just imagine, oh, computer can become smarter, right? Than probably than us, right? Because they can memorize more information than us. And they can not only memorize the terms, they can memorize the relations among the terms. And not only the class level, right? But also the instance level data. So, but they need something like this, like ontology, in order to become smarter. Otherwise, it's more like I tell the robot, I say I'm a human. The robot say, oh, you're a human. They don't know what's the difference between human and a monkey. But you have an ontology, they say, oh, human. Oh, yeah, you can think wisely, and you can probably kind of make a fire or something, which definitely is quite different from monkey. But anyway, so let's see how we do it. And okay. So let's say if we want to build an ontology, like say for AI, it's more like build an airplane, right? Like here we have a Delta airplane. Let's say we have an airplane like the 999. So how do we build the airplane, right? So let's say Boeing company want to build an airplane. So there are basically two methods. It's just okay, I'm just going to do it start from scratch. Well, start from scratch can be, scratch from scratch can be like, okay, you go to mine some kind of iron, like, and then start from the iron, or start from the raw material. But definitely it's not what they do, right? They buy parts. They don't buy raw material. They buy parts. Once you have parts, or some parts maybe you cannot buy from anywhere, then you have to build up. But once you have parts, now you need to assemble them together, right? So it's like building airplane. You need to design and assemble. You don't have to start from raw material. So what it means is like for example, I'm doing the coronavirus like ontology. I don't have to start to say, okay, I'm going to say, okay, coronavirus. I don't have to start to put those terms myself, right? Because there are already parts there. Like that's one, for example, the NCBI taxonomy. So they have about 1 million, 1 million different kind of species, right? And they have all kind of hundreds of coronaviruses. So you just borrow from them. You don't generate yourself, right? This is why we say we should bypass, not build parts. We should bypass and then assemble them. So, like for example, this is the example I just mentioned, the virus and the human, right? So basically, you can use you can go to, it's called a reference ontology. It's more like you go to grocery store, right? Or something is already coming from some big manufacturing, like 3M from the mask, for example. So you go there and buy them, right? So you just say, okay, I have several big ontologies. We call them reference ontology. And then you can basically go there and then bypass. So let's say I'm going to do a coronavirus ontology. I'm going to the NCBI taxonomy, to get all the terms of all the like a coronavirus branch, right? You can get hundreds of them. And then you can go to another ontology. Let's say the Uberon, another ontology. So they can see, okay, I have lung, I have like nose, mouth, the skin. So those areas can be useful to describe the disease. And then you can have disease ontology or drug ontology. They can have all the things there. And then once you buy those parts together, right? They don't build everything kind of closely for you. But after you buy the parts, it's not buy, it's free, basically it's free. You just import them, and then you can start to assemble all things together. So I just want to give you some example, like the coronavirus one. So as I said, like the NCBI taxonomy, it has about 1 million, 1 million terms, different all kind of species. So once you have we have a technology. I'm going to tell you because it's a tool, right? It's a tool demo. So we have 3 tools. So the one tool is called Ontofocus. So the Ontofocus is a pretty good one. So yeah, using the tool, you basically can easily, let's say if this is a branch, right? You can say, okay, I'm going to, ask for the top level, like a Cholera zero day, right? And then I can tell my program, I want to get the whole branch from the NCBI taxonomy. Then I can actually automatically get all the other things out from there. So then it's quite easy. Because if you don't have the tool, what do? You copy paste. So it's not easy, right? Because it's not only hierarchy, but it's also definition, synonym, and a lot of other details, ID, for each of the term, copy paste thing doesn't work. So unless you are super Java programmer, but every time you have to do it, it's just same kind of work. So basically our tool is Ontofocus. Later on I will show something. You can use the tool. Then so what you can get, right? It's like, oh yeah, we have the SARS-CoV-2, which is the pathogen for the COVID-19, right? So it actually belongs to the so-called subcov virus. So it's together actually with the SARS-CoV, which is the previous SARS. And then you have several, you have like a human coronavirus, HKU1, OC43, NL36, and 229E. Those actually can also cause human issue, but they are more like coldness, right? So, I got a cold, so that's kind of can be caused by them. And there are some other coronavirus like infectious bronchitis virus, IBV. So it only causes problem in chicken, but not in human. Previously, I got my education in veterinary medicine. So actually, I worked for 2 years. I see a lot of chickens died from the disease. That's terrible. But anyway, so the chicken have their own issue, so human have our own issue. Since I got the IBV for the human, so that's good way. So let's say, what about the host, right? So you can do the same thing with the host. So I have a student who annotated all the possible hosts, like human or reservoir host. Reservoir host means, they are just the middle level, right? They just pass the disease, maybe from bats to human. So we found more than 10 animals. They can all have been experimentally identified to have to hold, right, the virus. So interestingly, when you put them together, right, you have to use ontology to do so. Then you can find all the more than 10. They are all under the branch of what? Of mammal. So it's interesting because all the reservoir hosts or bats is also bats, right? Bat is also a mammal. So they are more like a mammal, like a human. So that was a paper they talked about snake. They said, okay, snake can be a reservoir host, but it's only by informatics kind of prediction. There's no solid evidence. So my feeling is likely not because snake is not a mammal. So because you can find some grouping kind of thing. So this is another like a usage of ontology. So we also did some work. So we found about 70 drugs that have been used to treat coronavirus, and with some success, maybe like in cell or in mouse model or in real human. So if I give you an Excel table, say, I have 70 chemicals, you probably say, what I should do with it, right? So actually, you can align them into ontology. And the ontology can tell you a lot of information. For example, ontology can tell you the mechanism of actions. So by aligning them into the ontology, actually, we found, like, for example, there's there's a drug, right? This is ribavirin. So it says has MOA, mechanism of action enzyme inhibitor. So when you put all the drugs there, some don't have the MOA information, but when you put them there, you can quickly find, oh, they are in this category. So you can find some pattern basically of the drugs. So it's a way to kind of annotate, the drugs and find some pattern. So why it's useful? Well, it may give you a clue, right, to design new drugs, and which can be used to treat the virus. So, but anyway, so this is some example to show how Ontology can help you to identify the virus and the host, and then how to deal with drugs. So, but it's more than that one. So let's say you have the virus, you have the host, you have the drugs. So they are kind of basically a small set, right? So you have to assemble them. You have to put them together. Once you put them together, you have to kind of make sure everything goes very well. So it's called interoperability, because otherwise, it's not only the term, right? It's also relations. The relation means hierarchy or means across different branches. So you want to make sure the interoperability, is good. So basically, the idea is like, okay, I want to build a cycle. I want to use it to study the coronavirus. And then how can I do it? So I basically say, okay, I'm going to bypass. What I mean bypass is like, I'm going to parts of the virus, right? And parts of the host and parts of the drug, right? I can do more. I can do the vaccine. I can do the transmission, pathogenesis. But then eventually, okay, I don't have enough data because, raw data are missing. But it's fine because I would say another example is ontology is more like the periodic table of chemical elements. So last year is the anniversary of 150th anniversary of Mendeleev's invention of the periodic table of chemical elements, right? So when Mendeleev developed the table, there was only 64 drugs, chemical elements there. So basically, he built up a framework. He put whatever he have into the framework, right? And then others he do prediction. So for ontology, I feel like it's similar. We can, build up kind of ontology. It can be for the chemical elements, or it can be for the disease, right? So you may find a lot of information already there. Then you can probably put it into ontology. You find the information missing, you probably can do some prediction. So this kind of idea, So in the end, like the periodic table, chemical element becomes the foundation of chemistry, right? So your ontology can become a foundation of the disease study, right? So this kind of idea. So you want to make sure, and also so much data around here. So you want to make sure all data can be linked. Maybe can refer to the ontology, and then all data cannot cross kind of shared, can be interoperable. So definitely this is a significance of how you can do so. So, and then now we know the interoperability is key. How do we do it? So we say, okay, this is the XOD principle and the tools. So basically the paper was published 2018. So the principle is actually not that complicated. It's basically 4 principles. So one is ontology term reuse. It's like, okay, I'm going to build my coronavirus infectious disease ontology. I want to reuse terms. I don't want to build up myself. I don't want to start from scratch. I don't want to reinvent the wheel, right? So you say, oh, the taxonomy. From the taxonomy, I can get the disease, the virus or the host. So I don't have to build up myself. I can go there and grab it. But the grabbing the terms, the branch is not easy. So, but you want to grab, you want to do it so. So we give you a principle, and then we give you a tool, right? The tool can help you very easily to do so. And then you have to do the semantic alignment. The semantic alignment, you can do it manually, or you can use a tool or if the two different ontology, because we are going by different paths, right? If the different paths by nature, in nature already align together, then you will make your job so easy. Just say, oh, I just get them, I just put them. I know it will fit, right? Sometimes it doesn't fit, then you have an issue. And then you can have, so this is kind of, you buy parts, right? But sometimes you cannot buy any parts from any company, right? For example, you want to build your airplane. So you have to build up yourself. So you want to build up yourself, you want to do it fast, you don't want to do it manually. Then we have a tool we call the, we have a tool, and then we have a principle first. We use Ontology design pattern. So you can have a design, you can have a pattern to be designed, and then use our tool to do so. So basically, then you can kind of make it the kind of airplane manufacturing much easier. But even though it's much easier, still a lot of time, a lot of effort. But definitely, it will be much easier. And then the community extensibility. So community effort is important because it's ontology work. You don't want to do everything isolated. You want to basically do it, as a community. So what you develop can be used by others, right? And then you can try to attract more and more, and even software developer to use your ontology. Then it's more useful. Okay. So that's kind of the 4 principles. And then here again, I would say how the principles can fit into fairness, right? So the fairness has the interoperable. So the principle is the key actually. The major part I feel like is to achieve interoperability, to achieve the efficacy. And then we have a few tools here. This slide is more like a summary of the tools we developed. We use something called Ontoanimal, and it's more like it's more the pattern. So you can see on the fox, on the dog, on the rat, on the bee, on the bird, etc. So basically, they save us all the time because when we develop it, we basically see that each animal tool is more focused on one specific task, right? And then you can put them together. So we see, okay, there's the term reuse. To make alignment, we can use onto focus. And then the term reuse, like on the dog can be used for term reuse. On the rat can be used for the ontology design pattern usage. And then we can have onto B, and several other tools. So onto B is it's the default server for the OBO foundry. The OBO foundry is it's a very significant community now. The OBO means open biomedical or biological ontology effort. The gene ontology was the first one of the OBO foundry, and now it has about 200 or even more than 200 ontologies. That's something we call the reference ontology, but most of them are reference ontology. It's something that it's more like you can go there and grab some terms and then you can align them to make your own airplane or your own ontology for your own study. So this one is more like how you want to build, right? So it's more like let's say we want to build up the coronavirus disease ontology. So you want to say, okay, we need a virus, we need a host, we need a cell, we need a kind of anatomy, and we need those pieces. Once we have those pieces, and then we need to assemble them, right? So basically, you want to build your coronavirus ontology. You want to basically, you first do a design, right? You just go to grab terms from different reference ontology, and then you say, okay, I cannot find any term from anywhere. Then you need to build up your own term, your own annotation, right? You can use the ontology, the new tool, format. I think it's it's good to give some demo later. But anyway, I want to reemphasize the principle one, the XOD principle one is term reuse. So you can reuse existing reference ontology to So it's more like, okay, I'm kind of doing the shopping, right? You want to go the shopping for the reliable kind of companies, products to do shopping. But we have a lot of reliable ontologies, like gene ontology and many others. And then this is the website for the primary use. This is the Ontofocus one. So because these two are basically, it's very easy to use. I don't know, let's say I can give a quick demo. So let's see. So here, this is on the focus, right? So let's say, for example, you choose one. So we have a lot. We have a lot of ontologies here. So let's say you want to say, okay, I'm going to find all the coronavirus to me, right? We go to see the NCBI taxonomy. So like NCBI organism classification, right? So you can see, okay, I can have a human. You can, let's say I like to have something called coronavirus. Yeah, so basically it will give you the hints. Let's see, yeah, actually the first one it is. So this term means this is a term and this is the ID. So let's say I'm going to choose this one, and then I'm going to say I'm going to add, right? You say I'm going to add this term, but I don't want. This is kind of high level term, right? I don't want to only have this term. Say I want to have the whole branch. So let's say you want to say, okay, I'm going to add this one for the include all children, right? You can say I'm going to include all children. What it means is like I have a branch, the whole branch automatically extracted, right? So you can say I can have annotation. You want to say you can have all exons or all annotation depending on what you want. And so you can do. Sometimes you don't want to have all children. Just say, okay, I just want to have myself. You don't want children, but you can have different options. You can have 3 options. Yeah. So once you do, it's actually quite easy. You just say, I'm going to get output. So just run it. Usually it's fine. It's quick, right? So yeah. So this one is like you want to put your children, your whole branch into some category of here. So, and then you can see I'm going to save the link, right? You can save it. You can use Ontology. This is a default ontology editor. But if you want to look for the source, it's more like XML, right? It's more like XML or RDF format or our format. This is our format. So basically, you just have a few lines of coding or play in there. You get tons of things. You get a lot of stuff here. So let's say this is Ontology, right? You can do the browsing. So we have, this one is I think my lab has developed many tools. And then the Ontology is likely the most useful tool. So we have a lot, probably about a couple hundred at least, IP address access every day, yeah. Okay, so, So let's say we have, I'm just going to the CIDO, right? Because we put it there. CIDO, this is so-called coronavirus infectious disease ontology. So yeah, I was using the Ontofocus to get the branch. So I think what we did is corona. Oh, sorry. Oh man. So yeah, we were doing the corona. Let's see. I just click anyone, okay? Because it's more like the branch, the hierarchy, right? So you can see here. Let's see. I want to get the real one. So all the human coronaviruses, they belong to this category. I think it's beta. Beta one is the beta. This is the Middle East respiratory syndrome related coronavirus. So this is MERS. This is MERS, right? So that's MERS, SARS. So you can, yeah. So you can see here, this is kind of how the virus organized. So this virus belongs to the, if you go further, right, it's viruses here. But you can kind of look deeper, it's the ribovirus, right? And then corona. So it's kind of different category. So then you can actually just a couple of lines by using our tool, you can get the whole branch of viruses. So it's like, oh, it's easy now, right? You want to build up, this is something we are actually putting a lot of effort doing now, actually. So we want to make sure we get all the pieces and we assemble them together. We make this one, and it can be very useful because it's a basis for a lot of coronavirus study. So it kind of defines a standard. Not only that one, it gives you knowledge. So, for example, it tells you, let's say if we have SARS, we have MERS, and then we have some virus that only, cause some colonies, right? Code. So, what are they? Similarity difference. They belong to different branch. They belong to different branch of the certain, right? So they may they may not be in beta. They may be in alpha. So they can be in alpha, or they can be in delta. So they can be in different places. And then you can see, oh, maybe the different branches, maybe it's the cause why they are pathogenic or they are so kind of a transmission kind of power, right? So this is more like the virus part. You can do the same thing with the host. You see, oh yeah, they are all mammals or something. You can even predict that maybe some mammal that can be the reservoir, right? And then you can look for the chemical. They can be the drugs. You say, oh, all the drugs, they belong to some category. So maybe we can try to invent some or try to repurpose some drugs, for the purpose of treating coronavirus or COVID-19. So yeah, this kind of the one idea. Okay, I just want to give you a quick demo for how the Onto focus. In some detail, it's like So this is in this example, it's the human, right? It's the eukaryota. It's the eukaryote is more like the eukaryotes, right? And then human. Surprisingly, from eukaryota to human or to mouse, in between there are about 40 layers in between them. Definitely sometimes you want to get all the layers because you want to know all the detail. Sometimes for some purposes you may say, oh, I don't care. Just tell me they all belong to eukaryota and then the others belong to virus. That's enough. So the tool, the Ontology tool actually can let you choose choose some option actually can tell you. But this one is everything, this one is no layer. This one is computed intermediate layer. So what it means is like, if I have human, rat, and mouse, actually I do have some layer. You don't need to add those middle things, but I'm going to catch them. So it's like the mouse and the rat has some common. The lowest common ancestor here is murine, right? And the murine and the human can have some lowest ancestor here. So they just have some mechanism or some algorithm to get whatever you need, but you don't have to be too simple or too complicated. So basically, the tool is one of the most useful tools now, is to kind of let you to go to a big ontology and grab, something, like, oh, I want to make an airplane, I want to buy some parts. You don't need to buy everything, right? Just say, I want to buy some parts. So, and then you can assemble, you can put this one into your own ontology. So this is kind of the principle one of XOD. Principle two is alignment. So I want to just make it simple because the alignment we can often do kind of manually, or we can the tool provides some capability for you to do some alignment. You need to do a little bit of coding, or you can basically have some other tool. So we have OntoFocus. OntoFocus is not a tool. So OntoFocus is like you can use the Excel format to do OntoFocus. Use Excel as an input. And then the XOD number 3 is based on the design pattern. The design pattern is like you have an Excel file, you have a lot of terms. You don't want to add the terms into your ontology manually. So let's say you want to say, okay, there's a coronavirus study. So you say I'm going to have a lot of kind of phenotype, right? I want to add them, but you probably let's say you have a lot, it's kind of tedious to add manually. So you can put it into an Excel file and design a pattern, and then use the pattern. You can automatically. So basically, it's more like how you can automatically, exchange your Excel file into ontology. So you don't have to do coding. You don't have to kind of manually put it in. So it's another tool so that can be quite nicely useful for you to generate new terms, right? So you have old term, you use OntoFocus. New term, you use OntoRead, and then you put them together, right? And now then you have a coronavirus disease ontology. Yeah, this community extensibility is very easy. You want to work together with a community. Yeah, and here is more like a summary. So we have kind of 4 principles. You have different terms. I gave a demo of OntoFocus. OntoRead, I gave a quick one. And then I showed the OntoB for kind of visualization. And yeah, so basically the essence of the list of tools is very simple because we don't have a lot of time and you give some background, but I just want to give you some flavor of how those things can be helpful. And then just because the coronavirus may give you some idea, right? Say, oh, it's just too small. You just initiated. Can you tell me some big project? So I can give you a couple of minutes to tell you how ontology can be used to support precision medicine. So there is the kidney precision medicine project. It has more than 20 universities. Just imagine like you get a patient's kidney tissue, right? Biopsy, you get data from everywhere. And then different universities want to co-organize. And then, different universities will do different study, right? So they can probably, let me see, I have here. So you have clinical data, you have molecular data, you have pathology data. They can be from different institutes doing the data. So how can those things put together, right? It is really not easy. Just imagine, it's not easy. So it's like this. So you have the omics gene expression data, imaging data, histology data, specimen data. And then you can have longitudinal clinical data. You can have raw data. How you can put data together into a very integrative analysis. So what the strategy we have is like, okay, we are going to get data from everywhere and have a data lake. And then we are going to build up, we can clean up a data lake, can make something called a knowledge environment. And then based on the environment, now we can do all kind of viewing analysis. But how to do it, So you will say, oh yeah, I don't care. I have money, right? It's a big project. I can hire people to do it manually. It's probably it will never work out. So you need to carefully kind of organize data, make standardized data, and you need to carefully find a way which is robust. And also you don't want to just say, okay, I just do KPMP's sake. It's just because you think KPMP is big, right? But there's another one. Maybe European has something KPMP-like project. They do, and China has one. And so many things, and then there's HCA1. And how your data kind of interacting, shared with their data, that is huge. So this is why we said, oh, we can use ontology, because ontology is a shared, is shared terminology, and it has a shared kind of semantics, and let AI, the robot, understand you better, right? So ontology is the key for the whole kind of KPMP project. Yeah, this one just give another example. So because like for the coronavirus, I tell you the virus and the host and the drug, right? But for the KPMP, for the kidney precision medicine project, we actually have more. We have gene expression, we have phenotype, we have cell line, we have tissue, we have all of them actually. So you can actually get a lot of points from different ontology. However, yourself, because it's like you say, okay, I have all the parts for my airplane build up. Can your parts fly in? No, right? You have to carefully put them together. Can they really fly? Well, yeah, or can the airplane fly safely and efficiently, right? So after you put parts, you have to build up your kind of links. You have to carefully link them together. So this is just one example. But I may have just one sentence. I say WT1 in podocyte is upregulated in the chronic kidney disease. It's just one simple conclusion of a paper or a few papers. So just a simple one, actually, you have to model them very carefully, but once you do so, then it becomes very powerful because it's only one, right? You can have hundreds of them doing this. You can have each gene expressed in some type of cells, in some organ, in some part, with some phenotype. So once you imagine, it's not only one; it's more like a network and hierarchical, and so it's horizontal and vertical. So it's a big network. Once you do so, actually you can do a lot of analysis. You can maybe just put a few lines. Well, of course, you say still you need programming. So the Sparkle is more like a SQL or MySQL, right? So to query vision database, this one is to query ontology. So ontology is more like you can represent it as RDF. So RDF is triples, right? RDF is triple. So you can put the RDF, you can put the ontology into triple store, right? And then you can query them. So the semantic is actually similar. So of course, people also develop kind of tools. They can put the Sparkle backend. So and then the common user, they don't even know ontology. They don't even know XML. They don't even know RDF. So they can still use it, but all the things can be on the ground and support kind of data integration, sharing, and cross different domain analysis. Yeah, I think that's it. So yeah, so the paper was proposed by my team and my collaborator, and all the animal tools, all the animal tools were developed in my lab over last about 10 years, and we have previous funding and currently funded by the KPMP project. So the PI is Matthias Kressler in our university, and I'm a co-I for the project. And the previous one, actually, we also work on several other faculty members, including Brian Azzi, Gail Oman. So like, I was a co-advisor for Sira. Sira is a Thailand student, K student, from Thailand. So Brian Azzi was major advisor. Gail Oman was his committee member. So we together we developed the cell ontology and also worked on the ontology of adverse events. So those ontologies actually are also developed using the similar idea, similar tools. At that time we didn't call XOD, right? It's just like 3 years ago we feel like we have so many Ontoanimal tools, people get confused. What's what, right? And then we say let's just get a way to put them together. So we get the idea. They have different functions. Then we call them Ontoanimal I mean, we call them SOD principles, and they have different purpose. But when you use all of them, then you can make a good ontology easily, and you can apply it for different applications. So yeah, that's all I have for now. Okay, thank you. Any questions?
No question.
No questions. That's fine. I mean, it's the perfect timing. I think it's like 1 o'clock. So okay.